Okay, we'll do this. This will be a short one. As people started to look in the world for how evolution really worked, and they would mimic it in laboratory experiments with things that reproduce really quickly, they would find that sometimes when the conditions changed, that there would be alleles in place that produced a tremendous advantage under the new conditions. Almost like they kind of got there when they needed to get there, which is what Lamarck thought happened in evolution, because he thought evolution was all part of God's plan and you got what you needed when you needed it. But that wasn't the way things were supposed to work. And people went, well, you know, this allele may have arisen many, many generations ago and it wasn't an advantage prior to this, and now it is an advantage. And people went, well, yeah, but I mean, that's a long time for it to hang around. Wouldn't it have just kind of disappeared over the course of that amount of time? Then Hardy and Weinberg came along, math people, statisticians, and came up with their rule, very often called Hardy-Weinberg equilibrium. And this is what it applies to. So you get a new allele, and it's going to be useful a long time in the future. They're going to say, well, if certain conditions apply, it's just going to hang around. If the population gets bigger, it will hold its ratio within the population, right? If I have a new allele, then some of my kids are going to get the new allele. And as the population grows and they have kids, is that even though, you know, there's nothing really happening to it, it does become found in more and more individuals. But it holds pretty much the same fraction of the population of alleles as it did. Well, what are the conditions that you need? Some of the alleles apply, or some of the conditions apply to the allele itself, and some of the conditions apply to the population, the gene pool, and the population that the gene pool is part of. Well, the first thing is, for a really, really long time, in terms of useful, not useful, it needs to be neutral. It doesn't need to give you, if it gives you an advantage, it's going to become more common. And the whole point here is that it didn't give an advantage until a certain point. And of course, the advantage could be survival advantage, natural selection, or reproductive advantage, sexual selection. Now, if you look at the original Hardy-Weinberg rule, it goes back like a century. They talk about random mating. And so they're using sexual selection under the old terminology, where people only thought about mate choice as terms of sexual selection. We don't do that anymore. So if I ask you this question, I'm expecting you to give it to me in the modern version and not the ancient original Hardy-Weinberg version, which means, you know, don't go find it on the internet, because that's a giveaway that you're not using the class materials. Now, one assumes that the allele started up because it was a change, it was a mutation. Change the code, change the protein a little bit and change the feature a little bit. But once you've got it in place, you can't change it again. And you know, that's not a big deal, because think of all the different genes. There's thousands and thousands and thousands of genes, and the odds of this particular new allele changing again are pretty astronomical. So people were like, yeah, okay, it could happen, but as long as it doesn't happen, no selection for it against it, no changing of the allele, then it'll hang around. This applies to the population. No splitting of your gene pool. where part of your gene pool goes off and goes somewhere else and now becomes reproductively isolated. Because chances are it's not going to be an equal split. If most of this allele goes with them, now it's suddenly a bigger fraction of that gene pool and a lower fraction of the starting gene pool. Also, if something happens and a big gene pool that's related to this one comes in and merges with it, that's going to mess with the allele ratios too. So this is kind of a mathy sort of thing. But it does turn out that migration is a big deal. And I'll throw some terms at you after we get done with the list that have to do with how the ratios do change if you apply this. Remember the need of big numbers when you're doing experiments? Because if your numbers are too small, just then weird, chancy things are going to screw up your averages. Well, the same thing happens with allele ratios. If your population is so small that only one member of the population is carrying this allele and a tree falls on them, then that kills the ratios. And also other things that affect this individual or that individual or this family can mess up the ratios for the whole gene pool if it's a fairly small gene pool. So Hardy and Weinberg did this, and people looked and went, oh yeah, I guess that could apply to, just an allele that arose in the distant past and just kind of hung around. As long as there's no push against it or push for it, as long as you don't change it again, as long as the odds work for you because it's a really big group and you don't splinter the group or merge the group, yeah, it would hang around. So it's no longer magically appearing when needed. It's been there all along. It just hasn't been obvious that it was there until it became selectable. So here's a couple of terms that go with this. So this is not the list. I'm going to write them both down. So say a small group from your big group does splinter off and go off someplace where they're now completely isolated from the original group. And the ratios of the alleles in that little group are different than the big group. Well, their new group is going to start with those ratios. That's the founder effect. If you look at Native Americans, you look at their blood types. Turns out blood type A is pretty rare in Native Americans. And the question is why? Has it got some sort of advantage, some selection advantage? Not that anybody knows. Some people have guessed that maybe, but there's nothing really confirmed. But it turns out that Native Americans originated from East Asia. Now it turns out blood type A is rarer in East Asia than your typical European background American population, but it's not as rare as it is in Native Americans. So here's the working theory. The Native Americans all originated from a fairly small offshoot of East Asia, maybe just a few hundred people, working their way along the coasts from Asia during the Ice Age when the water levels were lower to North America and then down into the Americas. Quite likely they worked their way along the coast in boats, decent sized, paddle-driven boats. We'll say your offshoot. You've got one family, and most of your A blood type alleles are in that one family. It's a fraction of the whole group, but it really is, it's going to run in a family, and it's going to be more common in one family than another. And that family just happens to, hit a whale or an ice, big piece of ice, and their boat sinks, and they all die. Now the fraction of A alleles in this population has just dropped by quite a bit. This is the impact of having a small group. And so now the ratio of A has gone from low in the original group to really low in the founder group. And all of the group that they give rise to are working off of that same starting ratio, that same low ratio of A's. Bottleneck effect is something similar, where again, you've got a small starting group and you're stuck with the alleles that you started with. But in this case, it happens when a population almost goes extinct, where something happens and most of the population dies out. And whoever's left, that's your starting gene pool. And whatever the allele ratios are in that, that's what starts the growing of the gene pool. Hamsters. Hamsters are all descended from just a small family of hamsters that were, well, first pulled out of the Syrian desert in like the 1880s or something like that. But most of them died. I think it came down to like 2 females and a male. And they gave rise to all of the hamsters that you can buy now, all the different varieties of hamsters, all go back to that starting group and their particular allele mixture. If you know anything about lethal genes, we're not going to talk about that. But it does impact the discussion if you get into it. So those kind of derive from the Hardy-Weinberg, which is why I'm covering them here. Now, the last part of the chapter, I do want to talk about about cancer as, because I already brought it up, and it does impact on this particular chapter. I'm going to do that on a separate video.